As AI becomes more capable, people increasingly find themselves competing with AI systems, particularly in workplaces where tasks once done by humans are now performed by AI. About 12.6% of U.S. jobs face high risk of automation-related displacement, and research shows this creates anxiety amongst workers. My research question was simple: does believing you're competing against an AI opponent lead to worse performance recovery after failure compared to believing you're competing against a human? This question is grounded in existing literature. We know competitive climates create replacement anxiety, and AI intensifies those concerns. Performance anxiety impairs working memory and slows response times. Learned helplessness theory tells us that believing failure is uncontrollable reduces motivation to recover, and prior research shows people make different attributions when they lose to AI versus humans. My hypothesis was that AI framing might accelerate learned helplessness. If you believe you're competing against a superior, unbeatable opponent, you might give up faster after losing. To test this hypothesis, I used Queens, a logic puzzle game from LinkedIn. It's a constraint satisfaction puzzle game where players place queens on a grid while respecting row, column, region, and adjacency constraints, and the goal is to solve it as quickly as possible. I recruited 30 participants and randomly assigned them to two groups. The control group was told they were competing against another participant. I avoided saying human to prevent suggesting a non-human alternative. The experiment group was told they were competing against an AI model. Participants were stratified by prior experience to ensure balance. On day one, everyone completed a puzzle and reported their time back to me. Then all participants received standardized failure feedback. They were told their opponent finished their game 20% faster than the participant's time. On day two, they completed a second puzzle and answered questions about their motivation and whether they believed winning was feasible. Performance was measured as percent difference from LinkedIn's global average completion times, which controlled for the fact that day two puzzles were easier than day one puzzles. Here's what the queen puzzle looks like. On the left is an empty board with colored regions, and on the right is a solved board with queens placed. I chose queens for 3 reasons. First, it's cognitively demanding. It requires working memory, spatial reasoning, and strategic thinking. Second, it's less ubiquitous than games like Sudoku, which could be an alternative, which helps minimize the impact of prior experience. And third, LinkedIn publishes global average completion times for each puzzle, which allowed me to normalize across puzzles of different difficulty. Here we get into my quantitative results. This chart shows average raw completion time. On day one, both groups performed similarly, about 208 to 206 seconds, well above the global average of 73 seconds. On day two, both groups improved dramatically to around 80 and 84 seconds, with the global average at 43 seconds. Raw times don't tell the whole story, though, since puzzle difficulty fluctuates. Thus, I normalized to percent difference from the global average. Control group went from average 186% difference from global average on day one to 86% difference from global average on day two. The test group went from 183% difference from global average on day one to 96% difference on day two. The key comparison is the improvement. How much closer to global average did each group get after receiving failure feedback? This chart shows that directly. The control group improved on average by 99.63% and the AI group by 86.52%. So the AI group did improve less, but the critical finding is this difference was not statistically significant. A two-sample t-test for significant difference in means yields a t-stat of 0.18 and a p-value of 0.855, very much insignificant results. The effect size, Cohen's d, was just 0.07, which is also essentially 0. A non-parametric Mann-Whitney U-test confirmed the same results. In plain terms, the two groups performed so similarly that any difference is indistinguishable from random noise. Qualitative data also supported this. Both groups reported similar motivation and believed winning was feasible. Interestingly, AI group participants cited the AI's reported completion time as evidence it was beatable, and participants in both groups attributed their day one loss to personal factors such as being tired, distracted, or nervous, rather than the opponent's unbeatable superiority. This suggests the failure manipulation didn't create the intended perception of facing an unbeatable opponent. So to conclude, this study found no evidence that AI opponent framing affects cognitive performance or past failure recovery. Both groups improved at virtually identical rates with negligible effect size. What does this mean? Brief competitive framing alone may be insufficient to trigger learned helplessness. Humans may be more resilient to AI competition narratives than the hypothesis predicted. There are limitations, though. The sample was small at 30 participants, and tracking change over a single day also has small sample effects. I also came to regret providing the relative failure feedback telling participants their opponent was 20% faster because this inadvertently communicated that the AI was beatable rather than superior, especially when the participant performed so poorly the AI seemed to as well.